Today we're doing problem 1818 minimum, the smallest, absolute tells you, well, it depends on what it is. Absolute is usually positive, right? Like absolute difference. The minimum, the smallest absolute sum is when you take things and you add them together, difference. So the minimum absolute sum difference, all right? Minimum absolute sum difference. You were given two positive integer arrays, nums1 and nums2, both of length n. All right, so we're given a little nums1 and a little nums2, and they're of equal length. Equal length usually, implies that we're going to be dealing with something where each index reveals something about both arrays, right? Because they're equal length, right? So they have the same amount of indexes, so each the index is kind of like revealing that they're parallel arrays or something like that. The absolute sum difference, we're going to call that ASD, is of arrays nums1 and nums2 is defined as the sum of nums1 of I minus nums2 of I for each 0 less than or equal to I less than n0 index. What does that mean? That basically means, for an array, we'll do this example actually, just because I like the way that it's written, and it's a little involved, but not too involved that it's going to be too time consuming, but involved enough that it's going to reveal kind of what the problem solution looks like. All right, 110.4.427 and 935.174. 935.174. The absolute sum difference is, well, you take the absolute value. Now, the absolute value is what? It's the positive version of anything, right? So we take the absolute value of each element at each index, and we find the difference, the absolute difference between each thing. So what does that mean? So we find the absolute value difference of the difference. We find the absolute difference between each of these indexes, and then we sum it together. So the absolute of 1 minus 9 plus the absolute of 10 minus 3 plus the absolute of 4 minus 5 plus the, I'm running out of space here, plus the absolute of 4 minus 1 plus the absolute of 2 minus 7 plus the absolute of 7 minus 4. Right, and that's all. Let's literally kind of listed right here. You'll notice there's some weird exchange going on, and we'll speak about that in a second. 1 minus 9 is negative 8, so the absolute value negative 8 plus the absolute value 7 plus the absolute value negative 1 plus the absolute value of 3 plus the absolute value negative 5 plus the absolute value of 3. Whew! And the absolute value basically just reveals the positive version of whatever it is, right? So what's the positive version of negative 8? That's 8. What's the positive version of 7? That's 7. What's the positive version of negative 1? That's 1. What's the positive version of 3? 3. What's the positive version of negative 5? 5. What's the positive version of 3? 3. And then we're going to add those together. And then you get 15 plus 1 is 16 plus 3 is 19 plus 5 is 24 plus 3 is 27. Okay, so that would be the absolute sum difference of this array. So we take nums1, nums2, since they're the same length. We can take each index, we subtract them, take the absolute value. We do that for all the indexes, and then we sum them together. Okay, but the minimum, well, we have the absolute sum difference, but we want to find the minimum. Well, I can't really minimize this, right? Because it just is as it is, right? There's these elements. I do this little operation, I get a value. Okay, so where does the minimum come in? That's this next little part. So you can replace at most one element of nums1 with any other element in nums1 to minimize the absolute sum difference. Okay, now that doesn't mean exchange. This means replace, right? So what are the candidates I can replace things with? Well, I can replace one with, well, itself, I guess. I can replace it with 10, I can replace it with 4, with 2, or with 7. I can replace the 10 with a 1, with a 4, with a 4, with a 2, for 7. So for each of these elements, I can replace it with any other elements, but I can only do that at most once, okay, within the same array. So this number has all these other elements as candidates to replace itself. This 10 has all these other numbers as candidates to replace itself. You can only do that operation at most once, okay? Return the minimum absolute sum difference after replacing at most one element in array nums1. All right, so basically you're going to replace the elements and then figure out what the absolute sum difference will be, and then maybe you could do that for all of them. Then you could find, what this value is and find the smallest one and just return that. One thing to notice is that at most one, so you don't actually have to replace anything, and that's what this example 2 shows, right? Because you notice the arrays are the same. So if you do 2 minus 2, 0, 4 minus 4, 0, absolute value 0. 6 minus 6, 0, absolute value 0. 8 minus 8, 0, absolute value 0. 10 minus 10, absolute value 0. Add them all together, you get 0. So you don't need to change anything there, right? It's already as small as it could possibly be, right? Because it can't be negative because we're doing absolute value, so everything's always positive. So I'm always adding together things that are either non-negative or positive or whatever. You know what I mean? The way I'm adding things together is, it can't get smaller than 0, your answer, and you can, walk through that if you don't believe me. But it can't get smaller than 0. So if it's already 0 when you have it, you have the perfect solution. You don't need to make any modifications, and that's why there's this idea of at most 1. With that said, let's think about what it means to make an exchange. So we can only make one exchange, right? So that's the first thing that you really need to think about when you look at this problem is only exchange once, okay? Not exchange, replace. Exchange means that you're swapping. We're not swapping, we're just replacing. Only replace once, okay? That's kind of the main idea of this problem because it's going to really limit what the result can look like, okay? So since we can only replace once, what would the score be if we replaced at any point? Okay, now this is saying that the answer is 20 because you're going to replace this 1 with a 9. Okay, now why? Wait, you're going to replace this 1 with a 10. Okay, so this becomes, remember the answer before was 27. Now the answer, we don't really know how to solve it yet, but it says to replace this 1 with a 10. You can't replace anything else if you've already replaced the 1 with a 10 because you can only do this operation again at most once. And what does that do to your answer? Well, this becomes 10 minus 9. Right? So then this becomes the absolute value of positive 1, and this becomes 1 instead of 7, so then our answer becomes 7 less, right, which would be 20. Right? Or just add these together again if you don't believe me. 1 plus 7 is 8, 9, 12, 18. Here, dude, 17. Oops. 1, 8, 9, 12, 17, 20. Right? So you'll notice just by making that little modification, by replacing this 1 with a 10, why can I replace it with a 10? Well, because it's one of the other elements I can use. Right? So it's one of these other elements. I replace it with a 10. I minus 9. I get 10 minus 9 is 1. Instead of getting negative 8, we get 1. This, instead of being an 8, is a 1 plus 7 gives it to 20. And that turns out to be the smallest operation that you can do. Okay? So you can only replace once. Okay. First question is to ask, what does that do? What does that do to my score? What change does that make to the score? Okay. Now you'll notice I didn't have to recalculate everything again when I made the change. Okay. Now the reason why this is important is you don't want to make a change and then calculate the whole array again, right? It's going to be far too slow because we're dealing with 10 to the 5 here, right? So we can't have a situation where we look at each element and we say, okay, we can only replace once. So let's go through each element, right? And see if we replace it, what does that do to our score? But we don't want to have to recalculate everything. And you'll notice here that I didn't have to recalculate everything. All I had to do was kind of nitpick through and think, okay, if I replace this, it's going to change this one number and change this one number, and I can be very fine and particular and precise, and I don't have to recalculate the whole array, right? I can just think about what it does to my problem as a result. Okay, so one way you can think about it is, well, if we have this array here, I'm thinking, should I do it in a general way, or should I do it in I'll do it in a general way because I hate myself, right? So nums1 and nums2. Let's just say in a generic way, it's A, B, C, D, E, F, G. All right, and this was H, I, J, K, L, M, N. You might ask me what am I doing right now, but I'm trying to show you kind of how this works and how you can, change one thing and not have to recalculate everything. So if we initially figure out what we call it, the absolute sum difference is. The absolute sum difference is the absolute value of A minus H. You know what? I don't like the way that I did that. Guys, sometimes you got to do better. So I'm going to call that, I almost did it again. I almost said, we'll call that N. I'm getting stuck on particulars here. It's fine. The letters were fine. I think I should just change the color and that'll be good enough. All right, F, G. So we'll make nums2 red just so that it's clear what's going on here. A, B, C, F, G, H, I, J, K, L, M, N. And our absolute sum difference would be A plus B minus A minus something plus C minus something plus dot, 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 dot. You get the point, right? And these would be the corresponding values in H and I and J and so on and so forth, right? That's the absolute sum difference, right? This is just the formula written out for a very generic example. Now, if I was to exchange B for something else, for example, right? If I wanted to make the swap at B, let's call that swap X, okay? If this is the absolute sum difference, well, A and H are going to stay the same. C and J are going to stay the same. D and K, E and L. Everything else in ASD, if I pre-calculate this, it's going to stay the same. The only thing that's going to change is here. Okay? And since it's the absolute difference, I don't want to think about, you know, can I just subtract B or add B? But you know what I can do is I can say, well, this is going to be ASD, what it was before. I'm going to call this ASD modified, okay? Well, that's going to be what ASD was initially, but this term is now different, right? Because I've swapped B for X. And since it's the absolute difference, I don't know like if I can just subtract B or just add B, so might as well just get rid of the whole thing because it's still constant. So it's ASD minus that B minus I, because that's no longer the case, right? Because I've changed the B minus I. And what I've added in instead now is this new term, which is X, where X is the value that I've replaced, from somewhere else in the array, minus that still same initial value I. Okay? So that's a constant way of modifying in place, and I can check each value, right? I can keep everything else the same except for the one thing that I'm changing, subtract out the thing that I changed, and add in what the change is now, right? So when I replace this B with an X, everything else stays the same. So I don't need to recalculate that. All I need to do is recalculate what the difference is when I add in X, and I replace this B with the X, and I subtract the I and get that absolute difference, right? So I can do that for each element in constant time, right? And that's all I did here, right? I pre-calculated this ASD value. Okay, so what I'm saying is, well, although it was minus 8, I mean, it was 8 before, right? So if I subtract out, if I say, you know what, this 1 minus 9 is no longer the case. So I subtract that out, right? I subtract out the 1 minus 9, and then what do I add in instead? I add in the 10 minus 9. Right, that's all I did here, right? This 1 minus 9, I subtract that out. And then I add in this 10 minus 9. So the original answer was 27, right? I subtract out the 1 minus 9, I get 19, right? 27 minus 8 is 19. So this becomes 8. This becomes 1. So I get 27 minus 8 plus 1, which equals 20. And voila, it's the same thing, right? So basically the idea here in general is to say, well, we don't need to recalculate every single time we find what we replace with this X value. We can just pre-calculate what ASD is, right? And then just use this little modification in constant time. Okay, so that's one part of the problem. But something, you know, the elephant in the room here now is, well, how do you calculate this X value? Right, you know, we have a quick way of using this X value and determining what the solution would be using this X value, but what would be the best X value for each I? Okay, and I guess the best way to answer that is to say, in this problem, why was 10 selected? Okay, why was 10 out of all people, out of all the people, of all the children in God's green earth, why was 10 the best person to put in this slot? Well, we want to minimize the difference, right? So if we want to minimize the difference between two things, we should make them as similar as possible, right? Min difference is the same thing as max similar. This is more of a logical concept here that I'm trying to articulate to you here. Don't look at that above. That's from a different problem. Okay, the minimum difference is the same thing as the max similar, right? If I want to make the minimum difference in people's heights, right? Say I'm matching people together, right? And they want to be really similar in height. Not like everyone else, but they want to be the same height for some reason, right? maybe they're dance partners. I don't know. Maybe dancing, it's ideal that people are the same height, right? Because you can look at each other in the eyes, you're proportional. Maybe your body parts are proportional. It's easier to, I don't know. So you want to match people together that are the same height, okay? Well, you want to make the minimum difference in height. Well, that would be their max similarity in height. So to make them, the minimum difference in height is to make them as close as possible in height. Right? Maybe one is a little taller than the other, or vice versa. But the minimum difference in heights is to make them as similar as possible in height. So the reason why 10 was chosen here is because it's the closest thing to 9. And since it's the closest thing to 9, it makes the minimum difference between them, which results in the minimum value here when you're summing the things up. Right? So the best person for 9 would be the person that's as close to 9 in nums 1. Right? Who would be the best for 3? Now, it isn't the answer to change the value here, but who would be the best for 3? Well, who's the closest possible to 3? It could be either 4 or 2, right? Because if you subtracted those together, right, initially it was 10 minus 3, you got 7. But if you subtracted 2 minus 3, you get 1. Or 4 minus 3, you also get 1. 2 minus 3, absolute value, of course, 1. Right? So the minimum difference is the max similar. So for each element, right, if we want to say, okay, we can only make one exchange, okay? I keep saying exchange, and I don't mean to say that. You can only make one replacement. If you can only make one replacement, then replace it with the element that is as close as possible to you and check if that makes your score better, right? So what you really do in this problem is you look at each spot, you look at each index, you pre-calculate ASD, of course, right? You look at each index and you say, what's the best replacement? That is the, closest element to nums 2 of index. You know what I mean. You know what I mean here. Closest element to nums 2 index in nums 1. Then you find out what your ASDM is by doing this calculation here. And then you say, is this better? Does that make any sense? No, it doesn't. That's why I hate pseudocode, right? But I'm basically saying is you can look at each of these things and say, who's the best here? It's the person that's closest, okay? Who's the best here? The person that's closest. Do that for each index, and whoever gives you the best answer would be the best exchange, right? Because you can only do this operation once, so try it at every index and see what you get, and whatever gives you the lowest number, that ends up being your answer. Okay, so what would be, so just to prove that to you here, right? Like you could try it here and say, okay, if I were to do this answer, my solution ends up being 20. All right. What if I do it at the next spot here? 10 minus 3. Well, what if I do instead 4 here? If I change that with a 4, the difference would be 1 versus the difference between 4 was 6. It's a plus 6, so I think it'd be 21. Here, there's nothing better for 5 than 4, so it would be the same answer, 27. And if you went through this whole line, what's best for 1? That's 2. Before it was 3, now it's 2, 1. So there's 1 difference. It'll be 26, and so on and so forth, right? But you'll notice that the best exchange happens here with this 10. So you can just go through each element, find the best X, and then see what your solution would be. And if that's better than whatever you think previously was your best solution, then you make that exchange. Hopefully that makes a little bit of sense. Right when we write the code, it'll help. But now I guess the only remaining problem is, well, how do we find this best X efficiently, right? I could look at each element and compare them, right? I could look at this 9 and say, compare this 9 to 1, compare this 9 to 10, compare this 9 to 4, to 4, to 2, to 7. That's going to be n squared time, right? Because for each index, you have to do this operation. So a better way of doing this, right? And we'll just go through this problem again. 1, 10, 4, 4, 2, 7, 4, 4, 2, 7. And we'll walk through this. 9, 3, 5, 1, 7, 4. Okay, we know that our ASD, what is it called again? ASD is 27 for this problem. All right, and then we'll calculate our ASD primes. Okay, we'll find our X values for each thing. And then our solution at the end will just be the best of this. So we'll keep track of that as we go. Okay, now we already know the value here is 10, but how can we find that efficiently without looking through everything? Well, if we first take nums 1 This is such a bad video. I'm all over the place. If we take nums1 and we sort it, we get 1, 10, 4, 4, 2, 7. Okay. And what we can do here is say, that's not sorted. So if we take that and sort it, what do we get? We get 1, 2, 2, 4, 1, 2, 4, 4, 7, 10. And all I have to do is say, okay, who's closest to 9? Well, what I can do is a binary search. In a binary search in log n time, I can find the closest element to anybody, right? Because what I can do is look at 9, and I drop this in this array at the center, and I say, okay, you're bigger than 4, so 4 might be your best option, because maybe all the other elements are like infinity or something, right? But I know for a fact if I'm bigger than 4, then I'm closer to 4 than I am to anybody shorter than 4, right? If I'm taller than you, and you're taller than all your friends, well, we're closer in height than I am to all your friends. Because if I'm taller than you and you're taller than them, then the height difference between me and them will be greater than the height difference between me and you. So when I look at, 9 looks at 4 and says, okay, you're 4, I'm 9. Everybody to your left, since this is sorted, is smaller than 4. So they're not going to get closer to me in height, right? You're closer to me than they are. So I can disregard these people and then only look to the right. And then he looks at 9, he looks at 7, and makes the same kind of calculation, and eventually he lands on 10 being the closest neighbor. Okay, so that's log n time binary search. And you can actually do that binary search in a prefix, not a prefix, it's called the bisect right. You can look at the code for that, but basically you do a bisect call here, and that'll give you the opportunity to find this efficiently. Okay, so basically you look at 9, you say, okay, who's the closest neighbor to 9? And you look inside of this array. You do a binary search here on nums2 of I, so at each index, right? And you say, okay, so for our x here would be 10. So our solution would be 27 minus what it used to be, 1 minus 9, plus 10 minus 9, because our x value is 10, and that gives you 20. So before I thought my solution would be 27, because that's what it initially would be if you made no changes, and now it's 20. Now I do 10 minus 3, so 10, what's better for 3? Well, then I do a binary search on 3, which would end up between 2 and 4, right? So I could do 2 or 4, would be the same here, right? So now it's 27 minus 10 minus 3, because I'm subtracting out what it was initially, right? That first thing we thought about. And I'm adding in, instead of 10 minus 3, now it's going to be 4 minus 3. So that's 27 minus 10 minus 3, 7. 27 minus 7 plus 1, which gives you 21. So I was right before, it's 21. So let me just look at all the x's going through. 4 and 5. 4, the closest thing to 4 would be either 7 or 4, right? But 4 itself is already closer, so it's not going to, or no, we're looking at 5 here, right? The closest thing to 5 would be these 4, so this is already as close as it can possibly be. So 4 would stay the same. 4 and 1, you look for 1, the closest thing to 1 would be 1 itself, so I could actually make this 1, right? 2 and 7, I could do 7. What's the closest thing to 7? 7. 4, the closest thing to 4 is 4. All right, and then you just walk through these calculations. I really don't want to go through, right? It's going to stay 20 here because 21 is not smaller than 20. Here you do 5 minus 4. Wait. 5 minus 4. It's actually going to keep the score the same because it's already the best thing that it can be. So it'd be 27 here. 20 still better. Here you could do, instead of 4 minus 1, you're going to do 1 minus 1. So you're going to get 0. So you're going to get 27 minus the application of this here, which is 4 minus 1. Now it's going to be 1 minus 1. So you're going to get 27 minus 3, which is 24. Right? So it's actually, you actually get the best thing you can possibly in the slot, but what was there before wasn't what's causing the greatest issue. So even though you get the best thing for this 1, the difference before wasn't that bad. So the score isn't improved, and so on and so forth. So we'll quit this. All right. So how are we going to do this? Well, we need to find out we need to have an array that we can bisect. So I'll just call that the bisect, and that'll be nums1 sorted. So take a sorted version of the list. So take nums1 and sort it. Okay. We need to find out what our absolute sum difference was initially, and that's going to be, you can do it like this. So we're going to take the absolute sum difference of all the elements in nums1 and A for A and B in zip nums1, nums2. So what this basically does is it just makes these parallel. So when you zip it together, it takes all the elements at the indexes and zips them together, right? So we look at all the elements in nums1 and nums2 together. We find the absolute difference. We sum it together. Our solution is what we're going to return at the end. And initially, our solution will be what's given, right? Because what's given might actually be the best, like in this example here. All right, now we're going to look at each index in the range of the length of nums1 or nums2 because they're the same. Okay. And then what are we going to do? Well, we're going to ask this question, right? We're going to say our new modified solution is taking our initial solution, right? We subtract out this particular index because we're going to make an exchange, right? So we're going to subtract out the absolute difference of nums1 of I minus nums2 of I, right? Because this was used in the calculation to calculate ASD. So again, it's the same thing that we saw. We're just going to remove that, and then we're going to add in what the best thing would be if we made this exchange, okay? So we need to find out what that X value is, right? The X value, we'll just say X is the index, right? We're going to bisect right the sorted system that we're going to bisect, and we're looking for the closest thing to nums2. Now, what I'm going to actually do is add in a float infinity just so that we don't go over, because basically what happens when you bisect something from the right is you can get too far right, and then you're going to look at something that's larger. Like something's larger than everything. When you bisect, you can look into the specifics of what I'm doing here. It's just, this basically just makes so I don't have to deal with edge cases, right? So it's never a bad idea to kind of, when you're doing bisects, some people might say this is a big no-no, but I don't really mind, right? But what I'm basically doing is I'm just kind of buffering this system so I don't have to deal with weird edge cases, okay? And you can think about that with the implementation of bisects, okay? So I'm looking for the perfect nums1 in nums1 that's as closest to the index that I'm looking at. And then I'm just going to figure out what that value is. All right, so it's either going to be nums1 of X. Well, it's not nums1 of X. Actually, the sorted system, because that's the value I'm looking for, minus nums2 at I. Or if, again, you probably need to look at the implementation of this because it could be either one, right? Because you could be in between two numbers, right? You could be, because what bisect does is it finds your position in the array, right? So I'm in between two numbers. So which of my neighbors am I closer to, right? That's pretty much what bisect will tell you. So I need to look at both of them. Am I closer to this neighbor or the one before me? Of I, okay? So, and my solution is just the minimum of whatever I thought my solution was before, and maybe this new thing gives me something better, and I just return that at the end. So actually, pretty sure this can actually move into here. Let's go ahead and submit that. Apologize about the quality of this video. I haven't made a video in a minute, and and like always, what does this usually mean? If you see a crazy big number and it's a smaller number, that's usually because you forgot to do what everyone forgets to do, which is modulate it by 10 to the 9 plus 7 at the end. All right. And usually you're in the clear if that's what happens. All right. So what is the run and space complexity of this? Space. N is the length of nums1, which is also the length of nums2. For space, well, we have to create this whole new array of size n, right, in order to reference it. And we can't use the initial array because we need to keep the relative order of things because we have to subtract out stuff. So that's big O of n, right, because we have to create this n array. And there's really no way around that. Maybe there's a cute way of doing it, but I don't know. For time, well, we have to sort this array. That takes n log n time, right, just standard sorting. And then we have to look at all n elements and we do a bisect. Bisect is a log n operation, right? So it's a log n operation, and we have to do that n times. It's another n log n. This is a constant operation. So that's n log n plus n log n. That's just n log n. All right, guys. Hope you guys have a beautiful rest of your day. I apologize for the quality of this video. Hopefully someone found it helpful. Peace out.